Welcome to this explainer on the fascinating world of sound reflection. Today, we're diving right into everything from basic physics all the way up to real-world acoustic engineering. We're going to look at how sound bounces, how we actually harness it, and how we control it. Have you ever walked into a totally empty room, clapped your hands, and just heard that sound linger in the air? Imagine standing right in the middle of a completely bare, unfurnished room. When you clap, you get this really distinct effect, right? That clap creates a sound wave traveling away from your hands in every direction. But because the room is empty, the sound seems to hang around longer than usual before slowly fading away. What you're actually experiencing right there is the fundamental property of sound waves interacting with the physical boundaries of a space. Okay, let's take a quick look at our agenda for today. First, we've got the bounce sound reflection. Second, nature's sonar, useful echoes. Third, we'll cover unwanted echoes and acoustic design. And finally, modeling the invisible. Let's get into it. Section 1. The bounce. Sound reflection. So think about a sound wave traveling toward a wall. It hits that wall and comes right back. It's actually exactly like bouncing a basketball off a concrete wall. Literally, the only difference here is that our sound wave isn't being pulled down by gravity. The crucial takeaway here is that when that sound wave hits a barrier and reflects back to you, we call that returning wave an echo. An echo is just the reflection of a sound wave. When you clapped in that empty room, the sound hit the wall, bounced back, and hit your ears a fraction of a second later. That's exactly what creates that cool, lingering effect. Now, different materials handle these waves in vastly different ways. Sound waves reflect best off of large, smooth, flat surfaces. Think glass, tiles, or smooth concrete. Honestly, this is exactly why you sound like a Grammy-winning artist when you're singing in a tiled shower. But on the flip side, soft, textured materials like thick curtains or wool blankets are terrible reflectors. They absorb and basically disrupt the wave instead of giving it a clean bounce. Moving on to Section 2, nature's sonar, useful echoes. So, how exactly does a bat hunt in total darkness? It's a pretty fascinating survival problem. I mean, if you can't see your prey, how on earth do you catch it mid-air? Well, nature's solution is an absolute marvel of physics, and it uses those very echoes we just talked about. Bats literally use echoes to track down insects. The bat lets out a really sharp, high-pitched sound. That sound wave zips through the air, hits the insect, and bounces an echo right back to the bat. By calculating exactly how long that echo takes to return, and sensing precisely which direction it came from, the bat instantly builds a highly accurate three-dimensional map of its surroundings. Out of thin air, it knows exactly where dinner is. And humans have essentially copied this exact principle with sonar on ships. A boat uses echoes to figure out the depth of the water beneath it. They send a sound pulse from the hull, it travels all the way down through the water, hits the solid ocean floor, and bounces back up. By measuring the time it takes for that echo to return to the surface, the crew can calculate the exact depth. But there's a really important mathematical catch when you're doing this sonar calculation. Let's say a boat pings the ocean floor, and the speed of sound in water is 1,500 meters per second. If it takes 0.2 seconds for the echo to return, you might think, okay, just multiply speed by time. But hold on, this sound is making a round trip. It went down and back up. So the total distance the sound traveled is actually double the depth. You absolutely have to remember to cut your calculated distance in half to find out how deep the water truly is. We even harness these useful echoes in modern medicine to literally see inside the human body. Sound pulses are sent into a patient's body. They bounce off different tissues and echo right back out to a receiver. This incredibly sophisticated method translates those tiny differences in return times into a visual map, which is exactly how we get an ultrasound image of an unborn baby. Section 3. Unwanted echoes and acoustic design. So, echoes are great for bats and submarines, but we actually spend a ton of time engineering our way out of unwanted echoes. Take music production, for example. If a note you play repeats with a harsh, glaring echo off a flat wall, your recording is totally ruined. That's why professional recording studios are practically covered in jagged, soft foam panels. And we see the exact same principle scaled up in massive theaters. The audience needs to hear the actors crystal clear, not a muddy blur of bouncing noise, so architects specifically design these spaces to eliminate any large flat surfaces that might cause destructive echoes. Think about it. If you have an empty room at home and you want to set up a drum kit without a terrible echo bouncing off every single wall, putting up flatwood panels or shiny metal sheets won't do you any favors. As we just learned, those are fantastic reflectors. To stop the bounce, you've got to cover those flat walls with soft, thick curtains or specialized acoustic foam. Basically, to defeat the echo, you have to defeat the flat surface. And finally, Section 4. Modeling the invisible. Because sound waves are totally invisible, scientists have to get creative to study how they actually reflect. You can easily prove these rules in a lab using everyday items. Imagine setting up a hard tile as a barrier and placing two hollow cardboard tubes at an angle pointing toward it. If you play a quiet tone from a phone down one tube, the sound hits the tile and bounces off. By moving the second tube around until the sound is loudest in your ear, you can physically map out the precise angle of that invisible reflection. The true beauty of this physical model is just how adaptable it is. You can swap out that hard tile for a piece of wood, or maybe some soft foam, and instantly observe exactly which materials are good at bouncing waves and which are terrible at it. We can even create a visual proxy for echolocation. Imagine a student using a flashlight and a mirror hidden under some cardboard. They play the role of the bat, using the reflected beam of light just like a returning sound wave to locate that hidden mirror. It's a brilliant way to make the invisible visible. I want to leave you with this final thought to test out your new acoustic engineering eyes. Take a second and look around the room you're sitting in right now. Do you see large, flat, hard walls and massive glass windows? Or is your space filled with thick carpets, plush couches, and heavy curtains? Based on everything we've uncovered in this explainer, is your room designed to bounce sound like a basketball or absorb it? Next time you clap your hands, you'll know exactly what the invisible physics around you are doing.